So section 4.5 is about the Hermitian operator. So we already discussed the condition for quantum mechanical operator. So in the postulate 2, second postulate, we assume that the quantum mechanical operator should be linear. In this section, we are going to add one more condition for quantum mechanical operator. So if you think about the form of the wave function or the operator, they can be mathematically complex number, right? If you think of the momentum in the x direction, that is like minus h bar d dx. So this contains the imaginary number. But in the laboratory, the result of a measurement, like when you're measuring the energy of the system or when you measure the position of the particle, that should be always a real number, right? Your measurement always gives you real numbers. So this physical necessity imposes a strict mathematical requirement for our operators. So this requirement is that all quantum mechanical operators corresponding to an observable must be Hermitian. So let's discuss what the Hermitian operator is. So Hermitian operator is the one that satisfies a very specific mathematical condition. So we are not going to prove the details, but the final outcome is the formal definition of Hermitian operator. So if you have a Hermitian operator A hat, so it is a arbitrary Hermitian operator. And there is two function, fm and fn. So if one says that the operator A is that Hermitian, then it satisfies the following integral relation for any two well-behaved functions. So it's like the integral so it very looks like the expectation value of the operator A, but actually this is not, because we have different function on the left and right side of the operator A. And there is another integral. So if these two integrals are equal, then we say that the operator A is Hermitian. So the postulate number 2 should be revised. So to every observable in classical mechanics, there corresponds a linear. So operator must be linear and Hermitian. So we already mentioned that when we discussed the postulate number 2, even though we haven't really discussed what the Hermitian is. So if you want to check some operators are Hermitian or not, then you can just calculate the first integral, left-hand side integral and the right-hand side integral, then to see if these two integrals are equal. So for example, like the operator A hat is d dx. So if you test this operator to be a Hermitian operator or not, you will easily realize that this is not the Hermitian. So this fails the test, and therefore this cannot represent any physical quantity. Okay. But there is like magic things happen. So if you multiply minus I h bar for this operator, now suddenly it becomes the Hermitian operator. So this satisfies the following integral equality. So inclusion of minus I h bar is precisely what is needed to satisfy the Hermitian condition. So making this operator A hat as a valid physical valid and successfully represent a physical quantity. So you all know that this is the form of the x direction momentum operator. So up to here we have discussed the Hermitian operator, and we are going to introduce a more elegant language in quantum mechanics known as Dirac notation. So this is also known as the bracket notation. So this is simply just another way to represent integral. So instead of f and x wave function, we will just use the cat vector, which is simply just like this. So subscript n is now here. And the complex conjugate of a wave function like fm star. So the complex conjugate of wave function is now called the bra vector. Bra. And we are using this notation. So for example, if you say just like you have a k cat, that means it represents fkx, something like this. So the way in Dirac notation, we can simply express the integral. So if you have an integral like this, this is very commonly appearing integral expression in quantum mechanics. So this is simply just a bra vector m and the cat vector n, like this. Quite simple, right? And if you want to insert the operator in between two functions, something like this, then this will be represented like bra vector m, operator n, a, and the cat vector n. So if we just use the Dirac notation, the Hermitian condition now becomes much simpler. So I have to write down the long and tedious equation. Something like this. But now we just write the left-hand side as the m, a, n. And the right-hand side, this is just like n, a, m, complex conjugate. So you might think this is not quite straightforward from the integral expression to the Dirac notation. But let's think about this complex conjugate. So if you take the complex conjugate of this integral expression, then that is just like Fn star A hat Fm dx, right? So this should be N A hat M. So it's a little bit complicated, but this is the complex conjugate of this expression. So if you take the complex conjugate again, then this becomes simply like this, right? So it is a little bit tricky, but this is the quite normal convention in quantum mechanics. So in the Dirac notation, we say that if the operator A is Hermitian, then we can claim that the operator A should satisfy this equality. So this is quite messy, so I'm going to write here again. Okay, let's move on to the next page. So even though we haven't discussed that what is the relation between the real number, like real number eigenvalue and the Hermitian operator, but if you try to remember and if you go back to your mathematical, what is the course name? The basic mathematics for chemistry, something like this, right? When you studied in the freshman. So in that textbook says that the eigenvalue of the Hermitian operator should be real. So it is already proved fact. So that's why we impose the Hermitian character for the quantum mechanical operator. Okay, and section 4.6 is about the eigenfunction of Hermitian operator. So the title says that the eigenfunction of Hermitian operator are orthogonal. So in section 4.5, we discussed the eigenvalues of Hermitian operators. And the most important thing is that the eigenvalues of Hermitian operators should be real. But 4.6 is about the eigenfunctions of Hermitian operator. So the remarkable consequence of Hermitian operator property is that the eigenfunction of Hermitian operator are orthogonal. So I guess you all know that the expression orthogonal. So it is the higher level of language or terminology of the perpendicular. So perpendicular is just like the 2-dimension or 3-dimension expression, and orthogonal is can be used in higher dimension. So let's consider two distinct functions, psi n and psi m. So this is the eigenfunction of operator A with eigenvalues an and am. So that means if you apply the operator A on wave function n, you will obtain eigenvalue equation something like this. And very similarly, you will obtain another eigenvalue equation for wave function m. So now we are going to show that the title of this section, the eigenfunctions of Hermitian operator are orthogonal. So first, let's take a look at the left-hand side. This one, left-hand equation. So multiply this equation by psi m star, the complex conjugate of psi m. And we are going to take the integral for both sides. And we cannot really do anything for the left-hand side because there is an operator and we cannot really change the direction or the position of the operator arbitrarily. But for the right-hand side, so an is simply the number, constant. So we can take this out of the integral sign. So that means I'm sorry, we have to put dx or any other integral, infinitesimal integral notation here. And okay, so this is our first equation. And let's try to play with the second equation. The second eigenvalue equation. So we are going to take the complex conjugate of the second expression. That means we have a hat psi m hat, star equal. So let's leave some space here because we want to do the similar thing for the first eigenvalue equation. So am star psi m star, and we want to find some relation between these two equations, these two eigenvalue equations. So for somehow we have to find some way to equate these two eigenvalue equations. So you might notice that by observing this equation, we can make exactly the same, not exactly the same, but very similar equation by multiplying psi n and psi n both sides and take the integral. So we cannot do really anything for the left-hand side, but for the right-hand side, so am star, even though this might be the complex number or not, this is simply just a constant. So we can take this out of the integral sign. Dx. So this is our second equation. So you might realize that this expression and this expression, the two expressions in the yellow box, they can be same if the operator A is Hermitian, right? They can be equal under the condition that A is Hermitian operators. Right? This is exactly the definition of the Hermitian operator. So we are interested in the eigenfunctions of Hermitian operators. So let we assume that the operator A is Hermitian. That means, so we now have the relation between the first and second eigenvalue equation. So as you can see here, by equating these two equations, we realize that the first expression and the second expression should be the same. And this should be so there is no operator here, so the multiplication order between functions are not really important, right? So we can change the order of the functions to be multiplied. So that means should be 0. So from our very first assumption is that there are two different eigenvalue equations. That means an and am. They cannot be the same, right? Because they are two different eigenvalues. So there is only one way to satisfy this equation. So in this equation, the integral should become 0. So this is the exact definition of the orthogonality between two functions, psi m and psi n. So for your conceptual realization, you might think like that these two functions are orthogonal to each other in functional space. So it is really hard to show you the orthogonal function in three-dimensional space, but you can just like accept like being orthogonal is very similar to geographical description of perpendicular. So, and I want to discuss one more thing. So there is some expression like orthonormality. So this expression is quite interesting. So it combines two characteristics of wave function. So the first expression ortho, that is from the orthogonality. And the second part, normality, comes from the normalization. So this expression is used to describe a set of functions that is both orthogonal and normalized. So we can express the orthonormality in a very compact way using Kronecker delta. Delta nm. So this is conceptually very similar to Dirac delta function. So it becomes 1 only when the n equal m. When n equal m. Otherwise, it is 0. So you might want to say like it's the integral between the complex conjugate of wave function m and n. This is if this function forms a orthonormal set, then this should be equal to delta nm. So when we have the same function, this represents the normalization condition. If these two functions are different, then this condition expresses the orthogonal condition. Okay, so now we understand the orthonormality. And let's move on to the next page to discuss the degenerate system. So the proof of orthogonality hinges on the eigenvalues being different, right? So we started with the two different eigenvalue equations. But what if the system is degenerate? So you all know that the expression degenerate, right? Degeneracy. So this means that two or more eigenfunctions correspond to the exactly one eigenvalue. So they share the same eigenvalue. So let's say the psi 1 and psi 2 share the same eigenvalue, a1. So in this case, if you think of the if you remember the derivation to show that two eigenfunctions are orthogonal, eigenfunctions of Hermitian operator are orthogonal, that relies on like something like this, right? Because now they both correspond to the same eigenvalue, so expression should be like this. But I mentioned that the eigenvalue of the Hermitian operator should be real. So this is exactly just 0. So this expression means that 0 multiplied by 1, 2 equals 0. So we cannot really say that the integral should be 0. Right? This is already 0, so this can be a finite number. So in this case, we cannot really say that if the system is in degeneracy, we cannot really say that two eigenfunctions form an orthogonal set, but there is always a way that we can make them orthogonal to each other. So let's try to understand the Gram-Schmidt orthogonalization. So even though we are not really sure that these two functions are orthogonal or not, we can make them a new orthogonal set. So let's look at the procedure. So first is to keep the first function. So let's say that the orthogonal set now contains the function p. So function p1 is just psi1. And now we want to construct the second function, and we define the new function p2. This is the linear combination of the two original function. So psi2 plus some contribution from the first function. Or you can just write like, because we set the p1 as the psi1. So step 3 is to enforce orthogonality. So we now want the orthogonality between the new function p1 and p2, right? So we write down the orthogonality like this, and we want this function should be orthogonal. So what we have to do is we have to determine the coefficient c, because this is the new constant we introduced during our procedure. So let's express this new condition with the original functions psi. So psi1 and something like this. So simply just this is the integral equation between the function, these two functions. So we know that the integral operator is the linear operator. So we can we can separate these two terms. Like right? This equation should be exactly the same. And we want this expression to be 0. So we know that the psi1 is already normalized. So this should be 1. That means the constant c, this is simply the the overlap between the first and second function and take the negative value of that function. So we determine the coefficient C. So this expression, the new function should be something like this. So even though it might look a little bit complicated, but this is very, very straightforward procedure. So if you have two vectors like this, let's say this is psi 1 and this is psi 2. And as you can see, these two vectors are not orthogonal to each other. And one way to make these two vectors to be orthogonal, you want to remove the component, x component in the psi 2 by projecting out the x component. So that means we are going to remove this x direction. That means the new function P2 should look like this. So how much x direction, how much the component x should be removed? This is determined by the constant c here. So the constant c is simply the overlap integral between these two functions, like projecting the second function onto the first function space. So we project the psi 2 on the psi 1. That is exactly the extent of the x direction amount to be removed in the second wave function. Right? So this is, even though this looks quite abstract, but if you have an analogy with geometry, like vector orthogonalization, that is quite straightforward. Okay, let's move on to the next page. Okay, section 4.7 is another math chapter. So if two operators commute, then they have a mutual set of eigenfunctions. So we are going to try to understand the uncertainty principle a little bit deeper. So that's the section 4.7 is a good starting point for that purpose. So now we arrive at a fundamental theorem in quantum mechanics that fully explains the relationship between commuting operators and their eigenfunctions and what it means to measure physical properties simultaneously. So you know that we cannot really take the exactly precise value for the position x and momentum x. And this theorem, the title of the section 4.7, this provides the ultimate reason why the uncertainty principle applies to the some pairs of observables, but not some are not. So the core principle is a two-way relation. So if the two Hermitian operators commute, if and only if they share a complete set of mutual eigenfunctions. So now we have a two Hermitian operator, and there is an if and only if condition. That means that we have to examine this statement in two way, right? So we have to examine that if the two Hermitian operators commute, then they form a complete set of mutual eigenfunction. And the other way is if two operators share a complete set of mutual eigenfunction, we have to examine that they are two Hermitian operator commute each other, right? So we have to examine two statements. So let's take a look at the first proof. So let's say mutual eigenfunctions imply commutation. So let's prove that if two operators A and B, if they have the same complete set of eigenfunctions, they must commute. Okay, this expression. So there is let's assume that we have a complete set of functions Pn, and they are the eigenfunctions of both A and B. This is our assumption here. So mutual eigenfunctions. So this is the complete set. So let's discuss the meaning of complete set first. So complete set means that if there is any arbitrary well-behaved function fx, if we have the complete set, that means that we can expand any function fx as a linear combination of our complete set. So we can make an equality like linear combination of our complete set. Then we can express any function using our complete set. Okay, so this is the meaning of complete set. And let's get back to our proof. So this complete set is the eigenfunction of operator A and B. That means something like this. And the second eigenvalue equation. So operator A and B, they share the same eigenfunction, mutual eigenfunction Pn, but they might have the different eigenvalue. Okay. So let's apply the commutator to the arbitrary function fx to see the impact of the order of applying the operators. So let's say like we want to discuss the impact of the difference in multiplying order on fx. So you may easily realize that this is simply the definition of the commutator. So this is simply the procedure to predict or calculate the commutator of operator A and B. So we want to expand the arbitrary function fx as the linear combination of the complete set Pn. So A hat, B hat. And they are just the operator, and this is the simple constant. So we can put this operator into the summation because the summation is the linear operator. That means you are going to have some expression like so you can apply the operator just next to the function p, right? That means you are going to have and apply here and apply here. So you remember that the complete set Pn is the eigenfunctions of both operator A and B. That means we are going to have something like this. And again, the eigenvalue an and bn, they are just a simple constant. So we can plug the operator into in between the simple constant and function. So I'm not going to write the every details, but the final result should be something like this. So you will easily realize that this value in the parenthesis, this should be 0, right? Because the Pn is the common term, and an bn minus bn an, they should be the exactly same, right? The multiplication order is not really important for the constant. So this value is simply 0. That means if we go back to the very first expression, so this is actually the result of the applying the commutator a and b on arbitrary function fx. So arbitrary function fx cannot be 0. I mean, this can be 0, but there is no way or there is no condition for the fx to be 0. But we have the equality for any time. That means the commutator should be 0. Right? So that is the proof for the first way. So if two operators share the mutual eigenfunction, they should be commutative. Right? So we prove that. And the second way is the reverse way. If the two operators are commutative, and we have to show that the eigenfunctions of those two operators should be the same. So commutation implies mutual eigenfunctions. So we assume that two operators are commutative. So let's say the commutator for the operator a and b is 0. And we are going to start with the eigenfunction of operator a, which we call PA. And let's say the eigenvalue is the small a. And we already assume that the commutator for a and b operator should be 0, right? So this is simply this expression. So if we apply this commutator on the eigenfunction of operator A, what would be the result? What would be the result of applying the commutator on function PA? Simply this is 0, right? Because the commutator is 0, so basically this equation is just PA multiplied by 0. So that means from this explicit expression, we can say that A hat, B hat, PA, that should be equal to B hat, A hat, PA. Right? And we know that if we multiply the operator A on its eigenfunction PA, then it should be so let's rearrange the expression, and left hand side is I put the parenthesis to imply to explicitly emphasize that the operator B should be applied first before the operator A. And the right hand side, I'm going to take out this constant. Okay. So let's take a closer look at this expression. So this expression is simply, so we apply the operator A for some, let's say, we don't really care about the explicit expression. Let's just say we apply the operator A on some function, the red box here, and we obtain the result is, what we obtain is the A multiplied by the same sum function. Okay? So that means this operator has the eigenfunction PA with the eigenvalue A, right? So that means this sum function in the red box, they should be just simple, they just simply the PA multiplied with some arbitrary constant, because the operator A should have the PA corresponding to eigenvalue A, and this equation exactly looks like something like this, right? That means this should be just PA multiplied by some arbitrary constant. Let's say this B. So I'm sorry. So this means, as you can see here, now we have two different eigenvalue equations. So operator A has the eigenfunction PA with the eigenvalue A. Operator B has the eigenfunction PA with eigenvalue B. So these two operators share the same eigenfunction, right? So where do we start? We start from this condition. Two operators are commutative. Then we arrive the expression that these two different operators share the same eigenfunction set. Okay. So what you might want to learn is that we know that Px and x is not commutative. That means do they share the same, or do they share the mutual eigenfunctions or not? They are not commutative. That means there is no common eigenfunction set for operator x and px. No mutual eigenfunctions. Okay, that's why they have some issues when measure the px first or position x first. Okay, let's move on to the next page. Okay, section 4.8. The title is quite long, so let's read the title first. So the probability of obtaining a certain value of an observable from a measurement is given by a Fourier coefficient. So the keyword is the probability of a certain value is given by Fourier coefficient. So we have established that when we measure an observable like energy or momentum, the only possible outcomes are one of the eigenvalues of that operator, right? So if you have the eigenvalue equation for a one-dimensional particle in a box, then whenever you measure the energy of that system, that is always one of the right? But if the system isn't in a single pure eigenstate, like the combination of many eigenfunctions, how do we know which eigenvalue we will get? So for example, like if you have a wave function like the linear combination of two different eigenfunctions, then how do we know which value we will get? So we cannot really say with high certainty, but we can precisely calculate the probability of measuring each one. So this corresponds to the energy h squared over 8 ml squared. So like when we measure the 100 times, we cannot really say for the first measurement, do we get the energy of this value or the higher value? We don't really know. We cannot really say that. What about the second measurement? We don't really know. It's all applied to the 100 measurement. But we can say that probability. So if I have to show you the final result first, like when we have the measurement like very small number, like the 2 times or 5 times, the probability should not be really follow the statistics. But if we measure like 1,000 times or 100,000 times, then the probability exactly follows the statistics. So we cannot really say which value we will get from the single measurement, but the probability is like the probability of having this energy value should be proportional to the square magnitude of the coefficient C1. Obtaining this energy is proportional to the square of the magnitude of coefficient C2. So when the systems are in a superposition of many different eigenstates, we cannot really predict the value from a single measurement, but we can say that for the large number of measurements, we can say that the probability should be related to the coefficients. Okay, let's try to understand this deeper. So the eigenfunction of the Hamiltonian psi n, they form a complete set. So actually this is very powerful mathematical property, which means that if you have any normalized valid wave function capital psi, then we can express this function as the linear combination or the superposition of the complete set. So sometimes we call this as the basis functions. So linear combination of the complete set. So we can describe any function of the system. So here we introduce the new constant. Actually, this is not the constant, this is coefficient. So we call them as expansion coefficient. So this tells us how much of the eigenfunction Pn contributes to the total state capital psi. So I want to be really cautious of using this expansion coefficient represents the portion of the eigenfunction psi n contributes to the total wave function psi, but actually the coefficient itself does not represent the amount of its contribution. So actually the contribution is proportional to the square magnitude of this coefficient. So I want to say there is like quote here. So Cn is somehow reflect the amount of its contribution, but the real contribution and precise value can be obtained from the square magnitude of your coefficient. Okay, let's take a look at why. So we have this relation. I'm going to write down this equation again. So the complete set of the eigenfunction of the Hamiltonian. So they form an orthonormal set. So if there is a complete set but not orthogonal or not normalized, then we can always make them as an orthogonal set, right? Because the normalization is quite easy, right? So we can take the square of the integrate the square of that function, and if you want to orthogonalize that function, you always use the Gram-Schmidt orthogonalization. So we can say that they are always orthonormal set. So we can calculate this coefficient Cn by projecting the total wave function capital psi onto the desired eigenfunction psi m. So this is simply multiplied both sides by psi m star and take the integral. So the left-hand side is and the right-hand side, we can modify the expression a little bit. So we know that the summation is the linear operator, so this can we can take the summation after the integral. And this coefficient is just a coefficient, just a number. We can take this out of the summation and the integral sign. So the right-hand side becomes okay. Sorry. Like this. And what is the expression we can use for this integral? We have an orthonormal set, so this integral should be simply Kronecker delta, right? And now we are going to take the infinite summation over the index n. So for here, m is fixed value, right? Because we select one eigenfunction, psi m, so m is the fixed index, but n is here, is the summation index. That means the n can be varied from 1 to infinity, right? So if you calculate the Kronecker delta, so this value always go to 0 except when n is equal to m, right? Otherwise the Kronecker delta should be 0, so we don't have any contribution. So that means Cn and this value is only give the non-zero value when n equal m, so that's why we have Cm here. Sorry, there should be summation here. Yeah. Okay, so we can calculate the coefficients like this by projecting the total wave function onto the desired eigenfunction. Now still you don't really understand the physical meaning of the coefficients, so let's try to understand them. Okay, so the physical meaning of the coefficients, physical meaning of the coefficient Cm. So let's take the calculation of average or expectation value of energy measurement. So we are going to start with the formula from postulate 4 and substitute the superposition for capital psi. So the expectation value of energy is simply so the operator, Hamiltonian operator, that is corresponding to energy measurement, is sandwiched between the complex conjugate of wave function and its original form. And we know that the capital psi, this is the superposition or the linear combination of complete eigenfunctions. So instead of capital psi, we can explicitly write down, actually we used small psi. like this. So that means complex conjugate, Hamiltonian, something like this. So I'm not going to derive the every details, but you can do this by yourself. So you all know that they are this. Actually, I don't really have to use the same index for these two summation. So let's say the second integral, a second summation, index m. Anyway, you know that these two coefficients are just number, and you can take this out of the summation. I mean, not the summation, out of the my explanation is a little bit wrong. So you cannot really take this out of the summation because this is affected by the summation index. Anyway, you can change the order between the summation and the linear summation and the discrete summation and the integral. I'm sorry that my heads are getting fuzzy. So the final expression should be something like double summation for the index n and m. So Cn star, Cm, Em, chronicle delta, Nm. So from this expression, we have the chronicle delta here. So we can run the summation index for m first. So that means for the given n, so within this nested summation, so only m can survive is when m equal to n. So this summation is now reduced to Cn star Cn. Now Em becomes En because when m is different from n, the chronicle delta should be 0. So which is exactly 1. And the final expression Cn square En. So from your understanding in statistics, the expectation value of E is simply can be calculated with the weighted average. So you multiply the probability of finding the system with energy En with energy En. So the first equality for the expectation value is from the quantum mechanics, and the second expression is from the statistics. They are from the different subjects, but they both express the expectation value of the energy, and the equality always should be valid. That means the square of the coefficients, the square of the coefficient's magnitude, it should be equal to probability Pn. So that's why we say that the square magnitude of the coefficients can be interpreted as the probability. So now you understand why I explained if you have a wave function that is the superposition of two eigenstates, psi 1 and psi 2, the finding the systems in energy of this much energy is proportional to Cn square, and this amount of energy is proportional to C2 square. Right? So this is the very important chapter, and you have to understand the difference between the measuring the single, take the single measurement and take the average of that measurement. This is a little bit, I mean, not really difficult, but can be confused. So please read the textbook carefully. So we have one or two section, but we have only 9 minutes. So let's call it a today here, and we are going to finish the chapter 4 next week. Okay. So okay, thank you for your attention, and let's meet next Monday. Thank you very much.